4.5, integration by substitution, day 2. So we're still going to talk about U subs, all right? But today we're going to talk about different ways we can evaluate definite integrals, okay, with U substitutions. So there's two methods that we're going to talk about, all right? And I'll show you those. Let's just jump right into it. Okay, so basically it talks about if the function u is equal to g of x, so that substitution has a continuous derivative on that closed interval, then we can still go ahead and say this, but notice our limits of integration have changed. Okay, so we can go about it this way. Like I said, I'll show you that method, or I'll show you both methods of what we can do. So let's just jump right into this first equation, or this first example. Okay, so we're going to evaluate this integral from 0 to 2 of x times the square root of 4x plus 1 dx. And we're going to use change of variable. Well, I'm going to show you two methods, okay? The first method is not using the change of variable. All right, so method 1 is just kind of keeping it as is, using a U substitution, and then eventually we'll substitute back. So I'll talk about this. So if we have our integral right here, okay, typically, you know, when we're trying to figure out what U is, we look what's underneath a radical or what's something funky happening to it. So we're going to let U be 4x plus 1. So then du is going to be 4x dx, so then 1/4 du is equal to dx. However, what we should notice is the integral still has this x in it, right? And also notice that these limits of integration are in terms of x, so we'll have to talk about those. But we need to take care of this x right here. So when we take care of this x, we have to remember, oh, since u equals 4x plus 1, what I can do is I can solve for this x so it's in terms of u. So we subtract 1 and divide by 4. So x is really equal to 1/4 times u minus 1. So we're going to substitute that back in for the x value up here. Okay, but notice now that I changed my limits to just a and b, because 0 and 2 were in terms of x, but we don't have our function or our integral in terms of x. So I'm just going to keep those a and b for now, okay? So now all I did was I brought this 1/4 out along with this 1/4, and that's where we got 1/16. We've got the integral from a to b, and now I'm just distributing. The square root of u is like u to the 1/2. And then we just distribute to u and to -1. So now we're looking at the integral of u to the 3/2 minus u to the 1/2 du, okay? Now, we're not going to evaluate until we put the function back in terms of x. So we're going to keep it a and b, okay? So as we integrate this, right? Integrating u to the 3/2, we get 2/5 u to the 5/2. Integrating u to the 1/2, we get -2/3 u to the 3/2 because of the minus there. All right, so notice I'm not evaluating it yet. We need to substitute back in for what u is, okay? So u is 4x plus 1, so I can make those substitutions, and now we can put our limits that are in terms of x back in and start evaluating this integral, okay? So when we go through that, now you can just kind of check the algebra here. So go through, when I plug in 2 for x, we're going to get 9. All right, again, 2 for x, we get 9. When we plug 0 in, we're over here, okay? When all is said and done, we end up with our answer of 149/30. So that's method 1. Method 2 is still changing the variable, which means we're then going to change the limits in terms of u, okay? So we don't have to worry about that a to b stuff. So we still let u be 4x plus 1, 1/4 du is still equal to dx, and x is still 1/4 u minus 1. But now we need to change our limits. So our limits went from 0 to 2 for x. So when x equals 0, I'm just going to plug that into our u equation. So then u is going to equal 1. Okay, so 4 times 0 plus 1. And then when x is 2, 4 times 2 plus 1, we get u to be 9. So now I'm changing my limits, okay, so that they're in terms of u, so that I don't need to substitute back in terms of x later on. Okay, so I kind of just jumped ahead. So we have 1/16 times the integral of 1 to 9 of u to the 3/2 minus u to the 1/2. We go through and integrate this, and now we're just substituting 9 in for u and 1 in for x, and you can see that it essentially gets us down to this line down here. Okay, so there's a little bit more upfront work because we have to change those limits of integration, but it saves us in the end as well. So it doesn't matter which method you want to take. I don't mind, okay? It's whatever you are comfortable with, okay? So if you have questions on either one of these methods, let me know and we can go through it. Now we're going to talk about even and odd functions and integration of these even and odd functions. So let f be integrable on the closed interval from -a to a. If f is an even function, so like this picture below, then the integral from -a to a of f of x is simply 2 times the integral from 0 to a, right? It's just double. It's symmetric, essentially. All right, but if f is an odd function, then the integral from -a to a is going to be 0 because part of it's going to be positive and the other half is going to be negative. Okay, so let's look at this first example or this second example where we are given this integral, all right, the integral from 0 to 4 of x cubed dx equals 64, and we're going to use that to evaluate without using the fundamental theorem of calculus, so just using the idea that it's an even or odd function to evaluate these integrals. So let's take a look at this first one, a. Okay, so if we have the integral from -4 to 0 of x cubed dx, okay, since x cubed is an odd function, we can go ahead and say, well, that's equal to the opposite of the integral from 0 to 4 of x cubed dx. And we know that the integral from 0 to 4 is going to be 64. So the opposite is -64. Okay? Take a look at b and see if you can figure that out on your own. So if we're looking at the integral from 0 to 4 of -x cubed, well, that's very similar to saying the opposite of the integral from 0 to 4 of x cubed. So again, we should get -64 as the answer. Okay, what about part C? The integral from -4 to 4 of x cubed dx. So go ahead, think about it, and let me know your answer. Again, since it's an odd function, we can essentially break it up. The integral from -4 to 0, which we know is -64, plus the integral from 0 to 4, which was given to us as 64. So this turns out to be 0, or if you look at the theorem up above, you could have identified that it was going to be 0 as well. Lastly, take a look at D, the integral from -4 to 0 of 5x cubed dx. Think about what this is going to be, come back and check. As you know, if we just have a coefficient, we can pull that out front. Okay, so it's 5 times the integral of -4 to 0 of x cubed, which we know is -64, so our ultimate answer is -320. These next couple of examples, we are going to solve the differential equation given what f prime is equal to and a point that it passes through. Okay, so remember, if we're solving a differential equation, that means we're solving for f of x, and if we're given f prime, f of x is just equal to the integral of f prime. So we're really solving the integral of negative sine of x over 2 dx. So what we should realize is we need a u sub. Okay, so typically we look on the inside. So we're going to let u be x over 2, so then 2 times du is going to be dx. All right, so now let's go ahead and make our substitution and evaluate this integral. Okay, so we make our substitution and we move things around. So we get f of x is equal to -2. I just pulled this negative coefficient out of the integral sine of u du. All right, well, integrating sine, we get negative cosine of u. And now don't forget that plus c, all right, because this is not a definite integral. All right, but now we're going to go ahead, clean things up, and substitute back in. All right, so now we have our function in terms of x. So in order to find our c value, we now need to use this 0.06. So we'll plug 0 in for x and set that equation equal to 6 to get our particular equation. And when I did this, I got c to be 4. So 2 times cosine of 0 plus c equals 6. Well, cosine of 0 is 1. So we get 2 plus c equals 6, and c is 4. So the particular equation is going to be f of x equals 2 cosine of x over 2 plus 4. I want you to try example 4 on your own using example 3 as a guide. Come back and check when you've finished. So as I went through this, my u substitution, I let u be 2x. So then 1/2 du is equal to dx. As we go through and we substitute in, we have f of x is equal to 1/2 times the integral of secant squared of u du. Well, the integral of secant squared is tangent of u, so don't forget to remind yourselves of those trig functions, okay? And so then our general equation is f of x equals 1/2 tangent of 2x plus c. In order to get the particular equation, we're going to go ahead and plug these points in. So x is pi over 2, and we're going to set the equation equal to 2. Well, tangent of pi is 0, so we get 1/2 times 0 plus c is equal to 2, so c is 2, and we get our particular equation here in the end. Example 5, very similar, just different equation. We're going to use this differential equation, dy dx equals 4x plus 9x squared over 3x cubed plus 1 to the 3/2 in the given point to find the particular equation. So the only difference is this is a bit more hefty of a function that we're trying to solve for, okay? So remember, if dy dx equals this function, then dy is equal to this function times dx, and to get y, we just integrate both sides, okay? Now what I did at the same time was I split up the integral to be the integral of 4x and then the integral of this whole piece here, okay? Now we can integrate 4x just fine, that's no big deal. But in this second integral, we'll have to do a u substitution. So I let u be the denominator because I realized when we take the derivative of 3x cubed plus 1, I'm left with my numerator times dx, which is perfect, okay? So those guys are taken care of very nicely with du, all right? So as we go through now and we integrate, well, first I can integrate that first integral. The integral of 4x dx is simply 2x squared, okay? Now I'm making my u substitution. I want you to try to see if you can finish this problem from here, okay? Integrate this integral, all right? Remember to substitute back for what u is, and then find the particular equation through the point 0, 2. Come back and check when you're done. Working through, hopefully you got your particular or your general equation to be this guy right here. That's as good as it really needs to get. But now we can plug in the point 0, 2, and hopefully you got c equals 4, and then our particular equation. I don't care which way you write it, all right? Either one is perfectly acceptable. Just recognize those represent the same equations there, all right? If you have questions, make sure you ask those. But we've got one more problem to do. This last example is asking us to find the area of the region shown for the curve y equals 2 sine of 3x minus cosine of 2x plus 1. In the end, we can talk about using our calculator to verify. So what does it mean to find the area? Again, the area just represents or is represented by the integral of that function, of that equation, okay? So it's asking us really to find the integral of what y is, okay, to integrate y. So one thing we should note is the limits of integration, 3.1416. Well, that's a rounded version. We're going to say that's pi comma 0, that endpoint. So if we're trying to find the area, we're simply trying to find the integral from 0 to pi of that function y, okay? Now, what we should notice, though, is there's kind of 3 sections, right? So let's go ahead and create 3 different integrals, okay? Because we'll need to. So if we do, we're going to get something like this right here. Okay, I'm going to move any coefficient out front. So 2 times the integral of 0 to pi of sine of 3x dx minus the integral of 0 to pi of cosine of 2x dx plus 1, or the integral of from 0 to pi of 1 dx. So what we'll actually have to do is we'll need to do 2 u substitutions, or I changed it to a v substitution for this second one, just so we have different variables. Okay? So for this first one, I'm going to let u be 3x. So then 1/3 du is what dx is equal to. The second one, we needed to make a substitution as well. So I just called it v. I let v be 2x. So then 1/2 dv is dx. This guy is no big deal. We can integrate 1 dx, no problem. So let's go ahead and integrate this. Okay, I tried to color code as best we could. So this 1/3 du, that 1/3 comes on out along with the 2. I'm changing my limits of integration because we're no longer in terms of x. So I just called it ab, sine of u du. Over here, we bring out the 1/2. We have the cosine of v dv. Notice I changed my limits of integration to c and d because now we're in terms of v, not u, and not x. So I used 2 different variables there. We integrated 1 and got x, and this we can evaluate right away on the interval 0 to pi. So now let's just go through and integrate each of these individually. Okay? So as we do, we are now here. So the integral of sine is negative cosine. So notice the negative 2/3 out front. Okay? I'm still integrating from a to b because I'm still in terms of u. I could have used change of variables, but I didn't. All right? Minus 1/2 sine of v. The integral of cosine is sine. And notice we're evaluating from c to d, all right, because we are still in terms of v. But when we evaluate x from 0 to pi, we're just left with pi. Okay, so now we make our substitutions back, all right? So for u, we have 3x. For v, we have 2x. And now we can go and evaluate that on our interval from 0 to pi. So as we go through, now it just becomes algebra, so be very careful as you're plugging in. Okay, and check what you get here. All right, so for this first function here, we're going to get cosine of 3 pi minus cosine of 0, essentially, and then multiply that by negative 2/3, subtracted by 1/2 times sine of 2 pi minus sine of 0, all right, and then plus pi in the end. So when all is said and done, we end up with the area being 4/3 plus pi. If you have questions on this, make sure you let me know. One last thing I want to mention is we do have a quiz coming up, so it doesn't hurt to remind us for another time what all of this is, the position, velocity, and acceleration, and the relationships between all 3 of those. So make sure you have that down and understand that. If you have any questions on this video, make sure you ask in class next time.